Today I am going to discuss about kinematics of a particle moving on a curve. As we have discussed in the previous lectures that a particle's position in space can be specified a vector. When the particle goes from that position to the another position, then there is a displacement. That displacement is change in the position vectors at two instants of time. If you differentiate that with respect to time, you get the velocity. Now, if the position vector can be expressed in terms of components along x axis, y axis and z axis, that is r is equal to xi plus yj plus zk, then it is very easy to find out its velocity by differentiating this with respect to time. So, therefore, velocity in this case will be dx by dt I plus dy by dt j plus dz by dt k. Here x, y and z are known as a function of time. Similarly, the acceleration can be found out by d square x by dt I plus d square y by dt square j plus d square z by dt square k. However, in many situations one may not know the explicit expressions for x, y and z as a function of time. Instead, it may be known that the particle is moving on a curve. Now, in this case, particle is moving, if the particle is moving on a curve, then its velocity can be given by v is equal to ds by dt et. This is very easy to see here, that if you have, suppose this is the origin, now origin is somewhere and this is the curve, this is origin O. At one instant of time the position is r, after that the position may become r plus this is next position. So, this is position one position, then you have got the another position, that is after time t r plus delta r. So, this difference is indicated by delta r. Now, if these 2 points are very close by, then delta r will be approximately equal to ds, that is the arc length. So, therefore, the magnitude is known as ds by dt E, and then the direction is tangential to the path, because as the delta r will approach the tangent as the distance between 2 points is very small. So, therefore, the velocity of the particle is given by v is equal to ds by dt et, where unit is the et is the unit tangent vector. Now, ds by dt basically represents the speed along the path. It is a scalar quantity that indicates s is the distance travelled by the particle. So, ds by dt is the speed, and et is tangential to the path. Therefore, et is given by dr by ds, that is unit vector tangent to the path. The acceleration becomes dv by dt. You differentiate velocity vector with respect to time. Again you get a vector quantity, that is this is a, and this is equal to d square s by dt square et, because you have had expression for velocity is ds by dt et. Now both are functions of time. If the particle was moving in a straight line, then et was constant, it was not a function of time, therefore its derivative will be 0. But in this case ds by dt is a function of time and also et is a function of time. So therefore if you differentiate, then dv by dt is equal to a, which is equal to d square s by dt square et, that is we apply the product rule for differentiation. First differentiated with this one, the second differentiate this et with respect to time. So you get another term ds by dt det by dt. So therefore this is the expression for acceleration, and the acceleration has got two components, that is one is tangential, that is d square s by dt square, it is nothing but the derivative of the speed. But the second component is very important, this is ds by dt det by dt. So let us see how we can simplify. Now det by dt is basically det by ds into ds by dt. It can be written like this. Therefore acceleration becomes d square s by dt square et plus ds by dt square det by ds. What does this expression show? It shows that the acceleration is composed of two parts. One part is tangential to curve and is equal to the rate of change of speed. The other part is in the direction of det by ds, which is the rate of change of unit tangent vector with respect to distance, and then there is a square of speed term also is there, ds by dt is the speed. Now if the particle is moving in a straight line, then et remains constant, hence the second part will vanish. So when the particle is moving in the straight line, this part vanishes because et is constant and it is not changing with respect to s, but first part remains. So therefore it is very easy to find out the acceleration there. But if the curve is not a straight, the second part will be present. Let us try to understand this part. Before we start discussion about that, let us review some concepts from the differential geometry. Now taking some concepts from differential geometry, now usually we have been studying planar curves, the curves which are contained in this, but in general a curve can be made in space also. So for example, you see that a curve has been shown here and there are 2 points have been indicated, those are P and Q, they are on the curve, and this curve is in a space, so it is a special curve, it is not a planar curve. In that case also one can draw a tangent on the curve at position S, this is ETS, and the next one is ETS plus delta S. So these are the 2 tangent vectors drawn this one. So a curve that if we can find out a plane which encompasses these 2 lines, that is ETS and this one, so this is called that, and if we keep the distance between 2 planes ETS plus delta S, the distance between 2 points is kept very small. In that case it is possible to find out the plane which will have these two lines lying in it, that plane will be called osculating plane. In this figure, at point P, a tangent has been drawn, that is called ETS. This is the situation at time r_t, and this is at time t plus delta t. Another tangent has been drawn. This is ETS plus delta s. PQ is length PQ is of length delta s. If the plane containing the unit tangents A, P and Q will become an osculating plane as delta s tends to 0. So, osculating plane may change from point to point or may remain constant. If the motion is taking place only in a plane, then that plane itself is a osculating plane. Osculating means kissing. So, osculating plane just kisses the path, that is why it is called osculating plane. Now, we define another plane, that is called normal plane. The plane passing through the point P on the curve and perpendicular to the tangent at the point is called normal plane. You see here at this point P, its position vector has been indicated by RT. Draw a tangent at this point, that is ETS, and this plane is perpendicular to the tangent line. So, therefore, this curve is coming out this side, and that side it has been shown by dotted. This plane is normal to the unit tangent at P and is called normal plane. Now, we define principal normal. The line that lies in the osculating plane passes through point P and is perpendicular to the tangent vector at P is called the principal normal. Now, in this case, this is a unit tangent vector, then this is a principal normal. Now, another plane is vector is defined, that is binormal. The binormal is the line that passes through the point P and is perpendicular to the osculating plane. So, binormal, like if this is a osculating plane, then binormal is downward perpendicular to the plane. This is shown here. Binormal is basically the cross product of unit tangent vector ETS and principal normal. It is a cross product which will be perpendicular to both these vectors. Now, after with these concepts, now we will develop an expression for the acceleration of a particle moving on a space curve. We need to find out the derivative dEt by ds. Et is the unit tangent vector. It is needed in equation of acceleration. Now, from the basic definition, dEt by ds is limit delta s tends to 0 Et s plus delta s minus Ets divided by delta s, which can be written as limit delta s tends to 0 delta Et by delta s. Here it has to be noted that difference between these two vectors will be a vector which has direction as well as magnitude, and therefore, the derivative of unit tangent vector is having the direction as well as magnitude. So, it is a vector quantity. Now this shows an oscillating plane. If we show a unit tangent vector at point S by ETS and another after the particle has travelled a distance of S plus delta S. So this becomes ET S plus delta S. The angle between these two tangent vectors is delta phi. If you draw a normal at S and similarly you draw a normal at this point, both the normals intersect at point O and this angle will also be delta phi. So ETS plus delta S minus ETS is the vector difference of these two unit tangents. Now these vectors have been shown along the path. This is delta S. As pointed out earlier, for small enough delta S, the line of action of the unit vector ETS and ETS plus delta S will intersect to form a plane as shown in the figure, and which this plane is called oscillating plane when delta S approaches 0. Now we have drawn normal lines to these vectors and they intersect at point O, which has been explained earlier. Now it is seen that as let us consider to see that what happens to point O as delta S tends to 0. The limiting positions arrived at for point O is in the oscillating plane and each called the center of curvature for the path at S. This is by definition. The distance between O and S is denoted as R and is called the radius of the curvature. Finally, the vector ET in the limit as delta S tends to 0 ends up in the oscillating plane normal to the path at S and directed towards the vector, this one, the vector delta ET in the limit as delta S tends to 0 ends up in the oscillating plane normal to the path at S and it is directed towards the center of curvature. This is explained here. It is seen that as this animation makes it clear, it is seen that as these are the two vectors ETS plus delta S, and this is the difference between them is indicated by delta ETS. As delta phi tends to 0, delta ET tends to be perpendicular to ETS. Because delta phi is tending to 0, these two angles are equal, both are unit vectors, so they are basically 180 minus theta divided by half. Now, as theta tends to 0, these angles become 0 in a triangle. So, this is what that happens. Now, we will now talk about the magnitude also. This let us see it again. See, this is what that is shown. The unit vector collinear with limiting vector delta ET is denoted as En and each called the principal normal vector. This is shown in the figure below. So, here this is ETS and another vector which will go towards center of curvature is indicated by En and this is called the principal normal vector. Now, when the limiting direction of delta Et, with the limiting direction of delta Et established, now we evaluate the magnitude of delta Et as an approximate value that becomes exact as delta S tends to 0. We observe the vector triangle in figure. In this we can write delta Et is equal to approximately Et times delta phi. This angle is delta phi, therefore this can be written as Et times delta phi, magnitude of Et times delta phi, magnitude of Et is 1 because it is unit vector. So this becomes equal to delta phi. Now next we note in this figure that the lines from point O to point S and S plus delta S along the trajectory form the same angle delta phi as is between the vectors ETS and ETS plus delta S, because angle between ETS and ETS plus delta S is delta phi. Therefore, angle between the normals to these two vectors will also be delta phi. So therefore, this angle is delta phi, and we can say that delta phi is equal to delta S divided by OS, which is equal to delta S divided by R, where R is the radius of curvature. Hence, we have Et is equal to delta S by R. We thus have the magnitude of delta Et established in an approximate manner. This is delta Et is equal to delta S by R. Therefore, we have established the magnitude of delta Et in an approximate manner. In an approximate manner, delta Et is nothing but delta S divided by R. Now, using En, the principal normal at S, to approximate the direction delta Et, because we can write delta Et is equal to delta S divided by R into En, where En is the unit vector normal to the tangent. Now, if we use this result in the limiting process, where it becomes exact, the evaluation of dEt by ds becomes dEt by ds is equal to limit delta S tends to 0, delta Et by delta S is equal to limit delta S tends to 0, delta S by R En divided by delta S, which is equal to En by R. Therefore, we can say that dEt by ds will be equal to En by R. That means, if you differentiate the unit tangent vector with respect to S, the magnitude of that differentiation is 1 by R, where R is the radius of curvature and it is in the direction of principal normal, that is En. Therefore, when we substitute this into equation of acceleration, the acceleration vector becomes A is equal to d square S by dt square Et plus ds by dt square divided by R into En. The second component always points towards center. It is to be noted that d square S by dt square can be a positive quantity or negative quantity. So therefore, the tangential component of the acceleration can be positive or negative. However, the second expression shows that ds by dt square is always positive, so the normal component is always directed towards the center of curvature. To show this point, this animation has been showed, displayed. This is now here. In this animation, the ball A moves on a curved path, reaches point B, then it reaches point C. Now, in this case, here at this point A, the particle A is accelerating on the, that means its speed is increasing. So therefore, the acceleration vector has been shown towards this side. That means, but the normal vector is towards the center of curvature. At point B, the particle decelerates. That means its speed starts decreasing. Therefore, the tangential component is along this direction. However, the normal component is still towards the center of curvature. At point C, also the normal component is towards center of curvature. However, the tangential component is along opposite direction. Now, so this expression is very important, that is A is equal to d square s by dt square et plus ds by dt square by r into En. We will be making use of this expression quite often. Now, we discuss motion in a plane and use the polar coordinates. This is a curve shown here, that is the trajectory of the particle, and at its position can be indicated by xy coordinates or by r and theta. R is the radial distance of the particle from the center O, and theta is the angle which its position vector makes with respect to fixed datum, which has been chosen here as x-axis. The polar coordinates r theta can be transformed in the form of x and y, functions of x and y. Now, we can define unit vectors ER and E theta established in the positive r and theta direction respectively. So, unit vector ER is along r direction and unit vector E theta is direction. The position vector r to the particle A has a magnitude equal to the radial distance r and a direction specified by the unit vector ER. So, although at this point we have two unit vectors ER into E theta, when we say that position vector of the particle, it is expressed only in terms of this position vector is equal to r times ER. Theta terms does not come here at this stage. So, it is very easy to sometimes specify its position by just one quantity. Otherwise, we have to specify x, y both. Here that this is shown here. Now, once we know the position vector, we can differentiate position vector and obtain the velocity. Velocity v is equal to r dot. Here dot indicates the derivative with respect to time, that is equal to, this r is a vector, that is vector, this is r dot, that is this is a scalar r, and into er plus r, which is a scalar quantity. This is differentiation of the unit vector, that is er t. Now, E dot r is basically dr by dt, because the particle is moving, its radial position keeps changing, therefore dr by dt will not be 0. dr by dt can be written as der by d theta into d theta by dt, that is equal to theta dot dr by d theta. Now, dr by d theta can be written as e theta. This point can be explained here. Now, supposing you have a unit vector er here, and after a rotation of delta theta, unit vector goes to the next position. Difference is given by delta er are in the limit. If delta theta is very small, this can be written as d er only. So, in this figure, magnitude of der is nothing but d theta, because these are the unit vectors. So, unit vector times unit length into d theta. Hence, if we find out the derivatives, so if we take the derivative of der by dt, it will be d theta by dt, that is theta dot, and the direction is along the theta direction. This can be explained very clearly, that as d theta tends to 0, direction of dr will be towards perpendicular to er. So, therefore, E dot r is equal to theta dot E theta. In the same way, it can be shown that E theta is equal to minus theta dot er. Here minus term is called theta dot is the can be written as omega. Thus, velocity of the particle in polar coordinate is written as r dot, which is r dot er plus r E dot r is equal to r dot er plus r theta dot E theta. Therefore, velocity has two components. One component is along the radial direction, and that is nothing but dr by dt, change in the radial radius, plus r, and another component along the theta direction, and that component r times theta dot. By differentiating this expression v with respect to time, we can obtain the expression for acceleration. Acceleration is given by a is equal to v dot, which is r double dot er plus r dot e dot r plus r dot theta dot e theta plus r theta double dot plus e theta plus r theta dot e dot theta. Now E dot r can be written as theta dot E theta, and similarly we know E dot theta also can be written as minus theta dot ER. So therefore this expression simplifies to r double dot minus r theta dot square ER plus r theta double dot plus 2r dot theta dot E theta. Unit vector ER and unit vector E theta both are orthogonal to each other. Now in this case we have, so acceleration has two components. One component is r double dot minus r theta dot square, another component is r theta double dot plus 2r dot theta dot E theta. Here we can see that if the particle is moving on a circular path where its radius remains constant, then r double dot will be 0. Even then there will be a component of acceleration along the radial direction, and that is equal to minus r theta dot square. Similarly, there will be tangential components. If the particle is moving with a constant angular speed, then r theta double dot will be 0, but still if the particle is moving simultaneously in the radial direction, then there will be another component, that is 2r dot theta dot E theta. In the cylindrical coordinates, the position vector of a particle is written as r times ER plus ZK. This is r is equal to r times ER plus ZK. Therefore, the velocity is v is equal to r dot ER plus r theta dot E theta plus z dot k, and the acceleration is given by r dot minus r theta dot square ER plus r theta double dot plus 2r dot theta dot E theta plus z double dot k. In spherical coordinates, we can employ the spherical coordinate also to indicate the position of a particle P. Here, three coordinate systems have been shown. This is Cartesian coordinate system indicated by x, y and z. Then we have cylindrical coordinates, and we have spherical coordinates. In this particle is at position P. Now in the cylindrical coordinates, its position is indicated by r, that is z, and theta. Theta is the angle which the projection of the position vector of the point makes with the x-axis in the xy plane. We can take, we have the position vector OP, take its projection in xy plane. This is making angle theta here, that is this one. So we, in the cylindrical coordinates, we have r theta z. Similarly, in the spherical coordinate, one coordinate is OP, that is the radial distance of the point P from O. Then we have got theta, then we have got phi. In this case, in spherical coordinate, its velocity is indicated by VR into ER plus V theta E theta plus V phi into E phi, where ER, E theta and E phi are the unit vectors along R theta and phi directions. VR is equal to R dot, V theta is equal to R theta dot cos phi, V phi is equal to R phi dot. Similarly, for acceleration, we have the expression acceleration A is equal to AR into ER plus A theta into E theta plus A phi into E phi, where AR is equal to R double dot minus R phi dot square minus R theta dot square cos square phi, and A theta is equal to cos phi by R d by dt R square theta dot minus 2R theta dot phi dot sin phi. A phi is given by 1 by R d by dt bracket R square phi dot plus R theta dot square sin phi cos phi. So these expressions are convenient when the particle is moving in a spherical path and you are asked to find out the velocity and acceleration components. Now we will be doing one simple problem to based on this lecture. So let us consider case of a particle moving on a circular path. Now this particle is going from this point to that around the circle. If it has been provided to you that in the beginning its speed is 0, so V initial is 0 and V final, its final speed is 250 by 9 meter per second. Then, and it has been mentioned that this particle attains a speed of 250 by 9 meter per second in 10 seconds. Therefore, we know that dV by dt is equal to 250 by 9 by 10, that is 25 by 9, provided meter per second, provided the speed has been attained in a uniform manner. Now, so we total time from this Vi is equal to 0 at t is equal to 0, this is at t is equal to 10 seconds. It is desired to find out the acceleration at t is equal to 8 seconds. That means find out acceleration at t is equal to 8 seconds. At 8, since the velocity is attaining the value of 250 by 9 in 10 seconds in a uniform manner, therefore the velocity after 8 seconds will be equal to 25 into 8 by 9, that is 200 by 9. So V is equal to, so V at that point will be 200 by 9 meter per second. Therefore, the normal component of the acceleration an will be equal to v square by r, where r is the radius of the circle. Supposing the radius of the circle has been given as 80 meter. So then you have got the component that is 200 by 9 into 200 by 9 divided by 80, which comes out to be 500 by 81 meter per second square. Then there will be tangential component of this one part. Tangential component at, its magnitude will be nothing but will be it is nothing but dv by dt, that is 25 by 9 meter per second square. This is per second square. Therefore, the magnitude of the acceleration a is equal to under root at square, that is 25 by 9 square, plus 500 by 81 square, which after simplification it will come out to be 6.77 meter per second square. Okay. Now let us discuss one or two more cases which will imply the concepts developed in this lecture. Now, it was mentioned that the velocity component in polar coordinate has two components, Vr is equal to r dot and V theta is equal to r theta dot. Similarly, the acceleration a can be written as r dot dot minus r theta dot square er plus r theta dot dot plus 2r dot theta dot. This is e theta. This is er. Now we will make use of this equation. Let us consider a problem in which there is a link which is rotating about this thing in a counterclockwise direction with constant speed omega. On this link there is a block which slides. This block is sliding on the link, that means it is going up, and link is rotating in the counterclockwise direction. So it is in the beginning, you may assume that in the beginning the link was somewhere here and the block may be at some position r. So after that block moves on the link, that surface, and at the same time its angular position is same as the angular position of the link. Therefore, the block's position is indicated by r times, that is er, that you have this is at any location you have radial. So therefore, it is very convenient to indicate the position of the block just by cylindrical coordinates. So this is a unit vector er, but unit vector keeps on rotating, so it is keeps on changing. In this case, just using the expression for acceleration we can see. Now if it is assumed that it is link is rotating with a uniform angular velocity, then there will not be any there will not theta double dot dot will be 0, theta dot will be omega. Then the acceleration of the block which is moving will be written as A is equal to r dot dot minus omega square r er plus r theta double dot, that is 0. So, therefore, 2 and r dot can be written as v, which is the relative velocity of the block on the link. So, it is 2v times omega e theta. Are you familiar with these components? We see that acceleration has got these two components. One is along the radial direction and another is along the theta direction. Along the radial direction, this is r dot dot, but as we already know that r dot is equal to v. So, therefore, r dot dot will be dv by dt. If the block slides on the link with a constant speed, then r dot dot this will also go to 0 and you will be left with minus omega square r er. That is, there will be one acceleration whose magnitude will be omega square r and it will be directed towards negative r direction, that means towards center of O. This component is known as the centripetal acceleration which the particle. Apart from the centripetal acceleration, you also get another component in the theta direction, that is 2v times omega. This component is called Coriolis component. So, when a block slides on a rotating link, we get another component of the acceleration, that is called Coriolis component, and its magnitude is given by 2v times omega, where omega is the angular speed of the link. If this comes due to sliding, if v is equal to 0, then this component will not be present. So, this is about the another. Similarly, so in general, when there are 4 components here, r double dot, that is basically dv by dt, then you have centripetal portion, then r theta dot dot which comes due to angular acceleration, and then there is a Coriolis component of the acceleration. Okay. Let us discuss one more problem. It is given that y square is equal to 10x is certain path. This is the equation of the parabola. X can be only positive, it cannot be negative, because y square cannot be negative for real numbers. So, this is shown here like this. Now, it is, if it has been told that S is equal to t by 2 plus t square by 100, and it is desired to find out its acceleration when y is equal to 10, y is equal to 10 unit or maybe 10 centimeter. At that point, how do we find out the acceleration. You have a known relation between s and t. S is the distance travelled by the particle. To solve this problem, we can find out the acceleration, one component of the acceleration, that is tangential component. We have developed these equations in the beginning. Let us go back to the previous slides. Here we have finally established this equation: d square s by dt square et. If you know s as a function of time, it is very easy to differentiate this and tell that this is the tangential component. Similarly, this is ds by dt whole square. This component can also be, if you know the radius of curvature, you can find out the other component. Now the point is that you have not been given time. So therefore, although you can take the derivative, but you do not find out the value of that derivative, you need to know the time. But it has been mentioned that y is equal to 10 centimeter at that point. So how do we tackle this problem? ds can be written as under root dx square plus dy square. Now s is equal to, we can write s is equal to 0 to y under root dx by dy square plus 1 into dy. That is the expression for s. Dx by dy can be found out from this, because you know x is equal to x square y square by 10. You can find out dx by dy square plus 1, and then you can integrate, and this can give you this thing. So you can get expression for s at that point. Then you know that this s is equal to t by 2 plus t square by 100. So solving this equation, you can find out the value of t. As you have found the value of t, you can find out the component of acceleration. How do we find out the radius of curvature? Radius of curvature for a planar curve is given by, this is 1 by r, which is called curvature, that is equal to d square y by dx square divided by 1 plus dy by dx whole square to the power 3 by 2. So if you know the equation of y, we can always find out this thing. So this is like this. Now we discuss one more problem. You know, in projectile motion, a particle is thrown. If you know, somebody says you find out the radius of curvature when the particle has moved top position. For finding out that, you know the velocity of the projectile at that horizontal velocity remains same. So with whatever velocity you projected, the velocity will remain same. Now v square by r is the normal component of acceleration, but which is nothing but g at this point. So this is equal to g. So therefore r is equal to v square by g, where v is the horizontal component of the velocity of the projectile. Using that, you can find out the radius of curvature. Although the radius of curvature could have been found by the equation of the parametric equation of the this parabola.